Okay, this is Dr. Joyce Miller again, and we're going over Lab Activity 7.1. This is Part 2, Question 2 for the pre-lab. So it asks us to determine the direction of the dipole for each bond and whether the molecule has an overall dipole by writing polar or nonpolar. Okay, so let's think about some polarity that you might be familiar with. You have a compass, and the compass we learned it always points north as far as while we've been here on Earth. There's been polar reversals, but right now the magnetism is that magnets are attracted to the North Pole. And so the same thing happens, or similar thing happens with molecules. The electrons are hanging out so that the electric charge is in a certain area of space. Now overall the molecule is neutral, but there's areas of the molecule that's more charged than other parts. And then we have to think, does this balanced out? Is this area that's where the electrons are distributed, is it balanced out so that the vectors always would add up to zero, the quantity of the charge and the directionality add up to zero as far as a vector goes? Or is it unevenly distributed, and so there's some areas that would, if you had a positive charge, would that molecule be able to go and line itself so that it would be in a position? So what I like to think about is if you had a polarity, if you had some kind of electrical charge, so you had a positive pole and a negative pole here. So you can think about electricity, and you could have something flow through here. So if you have this being positively charged, electrons are going to be attracted to this because opposites attract. And positive, the positive protons would be attracted to this side. So what we're looking for is an area in a molecule. Oh boy, there we go. An area in the molecule where it's going to be attracted to one area or not. Now overall, if we had an electrical current going through here, a neutral molecule would not move either way because it's neutral, so it's going to stay in space. But would it spin around so that the electrically negatively charged area, let's say it has a negatively charged area and a positively charged area, a three-dimensional, would it position itself so that the negative side is going to be closer to the positive pole and the positive side closer to the negative pole? Well, if it has an uneven distribution of electrons in 3 dimensions, it will do that. So let's look at these molecules here. So first of all, we have to look to see if there's an area that's going to pull the electrons closer to it than others. So once again, we go to our friend, the periodic table, and look at electronegativity. Carbon is more electronegative than hydrogen. So the electrons are going to be attracted to this. And so this is going to be like a positive area, and that's going to be a negative area. So let me draw that a little bit bigger here. This part here of this molecule is going to be positive, and this is an arrow showing the electrons are going to be pulled towards the carbon. So covalent bonds, which is what these are, they're sharing electrons, but they're not sharing them equally. They're unequal sharing. So the electrons are spending more time, because they can move in space, around the carbon than it is a hydrogen. So the hydrogen's like positively charged area. Now the electrons are still hanging around here, and maybe every once in a while in time there could be an electron on the outside, but most of the time the electrons are going to be in between the hydrogen and carbon nuclei, and they're going to spend more time by the carbon. So the same thing for these hydrogens. So we can draw positive and positive here. So if you were to add up all the vectors and the amount of charge, they'd all equal 0 because they're all going this way. So there's no area on the outside of the molecule that's going to be more negatively charged than another area. So this would not be attracted, it would not stay in space. Back to our little diagram here with our poles, it wouldn't position itself so that any hydrogens would be closer here because the hydrogens would be repelled here, so it kind of just would like spin in space. It wouldn't align itself because all these add up to 0. So now let's look at the next one. Once again, those hydrogens are going to not be able to pull the electrons to them. They're going to be unevenly shared. And so, but then we have chlorine with it. It was a very powerful electronegative atom, and so the positive part is going to be by the carbon, and it's going to be more negative here. So we've got an area here where the electrons are going to be hanging out here more than they are in any other part of the molecule. So this is going to be an area that's negatively charged. These areas are going to be positively charged. So it can align itself in our pole thing where the chloride is going to be hanging around here, and the carbons and the hydrogens are going to be here, and it's not going to spin around because it's going to like the position it's in. So the vectors don't add up to 0. And once again, it's very important for you to realize that this overall molecule is neutral. So it's not going to travel closer to the one pole than the other. It's just going to align itself. Now I kind of made it look like it's a little closer, but I shouldn't have done that. It's in the middle because it's neutral. Okay, so there's that. So now we have the same thing here where we have a chlorine, and it's going to be more negative, and this chlorine is going to be more negative, and the carbon's going to be more positive, but this carbon's going to be more negative, and this is going to be more positive here. So we have some unequal distribution, but the vectors, if we were to say, okay, this vector is going in this direction with this amount, this length, because the length represents the distribution of electrons. So the direction would be this direction, and this one would be the parallel direction, but in the other direction, and at an equal length. So these two vectors and these vectors would all add up to 0 because this is going in opposite directions and equal strength, because the chlorines have equal pull for the electrons, and the carbons have equal pull from the hydrogens with the same direction and equal distance, you could say. So the vectors all add up to 0. So now your goal is to look to see if there would be an area in these other molecules. You draw the electronegativity, so you would say, okay, is this going to be positive, and this is going to be negative, and this is going to be positive, and so you see if things add up. Well, here you have a linear molecule, but perhaps the oxygen, the vector for it, while in the opposite direction of the hydrogen, is a longer one because it has more pull. The length represents the strength of pulling the electrons towards it. So the directions maybe cancel out, but the amount of pull doesn't cancel out. So this could be polar. So this would be nonpolar, this would be polar, this would be nonpolar. So when the vectors add up to 0, it's nonpolar. When they don't add up to 0, when you think about just a qualitative length, assigning the length as far as the strength of the bond. So you have to look at electronegativity, look at whether there's any unshared pairs of electrons, and see if there's some polarity there for those. So if you have any questions, you can find me in the lab on Monday, Tuesday, Wednesday, and Thursday, or you can email me or come to my office. Hope this helps.